Starting recording. So, you know what? Why not? Yeah, I got all sorts of Christmas music. Yeah, that's a really good idea, Andrew. I will start playing Christmas music in November. It's November. Oh God, it's November. Okay, yeah, yeah. When normally I would not want to play any Christmas music before like the 1st of December, but maybe the last week of November I'll move it forward. Oh, start playing it ASAP. How many other thing? Okay, so maybe we'll be like the one place where you start Christmas music early, and we'll go from there. You know what? Good. Start Christmas music next class. It's new week, right? Okay. So we're done alkenes for a bit. We're not done with alkenes. We'll be visiting them again. But we're going to move on to a different type of double bond, and we're going to talk a little bit about carbonyl chemistry. This is a new component in this course. We haven't traditionally taught carbonyl chemistry in this material. The reason why we're moving it forward is for some students who go on to do the MCAT, and this is their one real organic chemistry class. There's a lot of carbonyl chemistry there. It also builds for those of you who do not take organic 2 but do take the biomolecules class. Um, a lot of that relies on carbonyl chemistry. So again, we're taking more of a chemistry perspective on it here, but it kind of plays into all these reasons, and that's why we're introducing it now this year into this course. So there we go. So what is a carbonyl? We've been talking a lot about them. They are a C double bond O. So these are found in ketones, they're found in esters, aldehydes, amides, acid chlorides, acids, all sorts of things. But it's this bond that we're talking about. And if we remember what this is, we're looking at this kind of sigma and pi bond interaction. And we have p orbital interacting with the p orbital, making a pi bond, or you can label that 1/2 pi, this 1/2 pi, that's sigma. Excuse me. I'm allergic to carbonyls. So, whenever we have a bonding orbital, we also have an antibonding orbital. And if we look at the carbonyl antibonding orbital, what we have is we kind of have the two p orbitals kind of pointing away from each other. I'm just going to draw a bond there for the sigma because I really want to focus on the pi bond. And this is your pi star or your antibonding orbital. And what we have here is we have no interaction. Now, almost all the time that bond's empty. There's no electrons in the antibonding orbital. Like it's kind of there, but nothing's there. It's kind of like an empty penthouse apartment. Now that analogy is not going to work. I really don't have a good one. But it's empty. But if it suddenly becomes occupied, you break. Maybe it is like a penthouse apartment that's right above you. If it suddenly becomes occupied with a party, you don't want to be in your apartment anymore, so you break your bonding orbital. So we've talked a lot about that in the beginning of the class. I'm not going to belabor it again here. But one thing I'm going to point out, and we've talked a little bit about this, and we're going to move into it more when we talk about SN2 and SN1 reactions coming up, is a lot of chemistry happens because you put electrons into the antibonding orbital. So I'm going to highlight right now is this angle here is about 107 degrees. I'm going to write that bigger so you can see it. This angle is 107 degrees between the sigma bond and kind of the because of the V vector of the antibonding orbital. The p orbital is about 90 degrees. The antibonding one squishes away though because it doesn't. It's repelled by the other antibonding orbital because unlike phases disrupt each other. Yeah, that's supposed to be a no. I just can't finish a curve. So one way we can draw this maybe a little bit more accurately is I'm going to make the O orbital bigger. In the bonding orbital, and the O orbital smaller in the antibonding orbital. So why is that? Well, it's not actually bigger, but we're not actually drawing. There's no actual p orbital in a bond. You have these molecular orbitals, and these are all models, right? We're kind of drawing this. But in the bonding orbital, when we think about the carbonyl, that bond is quite heavily polarized. There's a lot of that negative charge sitting over by the oxygen, so it makes sense that there's a higher probability of finding electrons in that bond over by the oxygen. We're going to represent that by making it a bigger lobe. What this means, of course, is carbonyls have awesome resonance. Where you get this resonance structure. So we always have to consider this resonance structure, and this is what drives the reactivity of carbonyls. Okay, so what do these carbonyls do? So what I want to talk about first is I'm going to talk a little bit about it's all the same reaction. And what we're going to do is we're going to use the carbonyl as an electrophile. So when we were talking about the double bonds, the alkenes were almost always a nucleophile. We were using the electrons in a double bond to attack something, which then gave us these three-membered rings and all that stuff and positive charges and what have you. Now we're going to actually use them as an electrophile, though. And that's because the antibonding orbital for a carbonyl is quite low-lying. It's quite accessible. And so if we take something, I'm going to start with what's called a Grignard reagent. This is notable because it is one of the only reactions that is named after a graduate student at the time instead of the principal investigator. Professors take all the credit for everything, and grad students take all the blame. It's, praise flows up, shit flows down. Standard operating procedure. That's starting to change now. What's really important is this came from the 1890s, and so somebody kind of gave up naming rights, and the grad student got named after. This got named after the graduate student. What they found is if you took a carbonyl, we're going to just use acetone, and you treat that with what's called a Grignard agent. What makes it a Grignard agent? A reagent. It's this magnesium bromide thing. You get, and then water, then water afterwards, water workup. You get that. So what we did is we added a right methyl. We added the methyl group to the carbon and broke the carbonyl bond, made a carbon-oxygen single bond, and made a carbon-carbon bond. So what's going on here? Well, let's take a look at what we've got in the way of reagents. So if we take a look at the acetone, we were just discussing this. We have this really good resonance structure. Like, it's not as good as, having no bond because you got charged and everything, but your charges are all right. Like, you got the negative charge on oxygen, a positive charge on carbon. It kind of makes some sense. Now, this methyl magnesium bromide thing, what does that actually look like? Well, you got a methyl group, CH3. making a bond to magnesium, which is making a bond to bromine. And this is magnesium 2. For those of you who like counting this at home. Yeah, it's magnesium. Like the metal, magnesium. So this is magnesium 2. If you look in your periodic table, find magnesium. It's in the second column. Um, Alkaline earth metal, whatever. And that means that it likes giving up 2 electrons. So it likes being magnesium 2. So this is a very natural state for magnesium to be in. And we can kind of think of this. Oops. Are these one question is, are these bonds covalent or ionic? My answer to that is yes. Those bonds to that metal are kind of in between being covalent and ionic. So if you want, you can think of it kind of like CH3 minus, magnesium 2 plus, Br minus. So if you want to think of it that way, that's cool. And the way we actually make these, we used to, normally we would actually consider doing this as a lab in this course, is we take something like methyl bromide. The CH3 is the methyl. That's what methyl means. Is that good, Michaela? Okay. And we add, okay, awesome. And we add magnesium metal. I'm just saying magnesium 0 because it's metal. And it kind of sticks itself in between the two. And anyone who's really interested can come to office hours for the mechanism. I'm not going to ask you about that. You can look it up if you like to, but I'm happy to talk about it. That's kind of beyond the scope of what we're doing. Sort of a sidebar. I shouldn't actually circle it and not say sidebar, because if I circle it, it looks important instead of less important. They discovered that the chemistry happened in the 1890s. Actually, I can look up exactly when it happened. It actually won a Nobel Prize. So the first paper was published in 1900 in French, and it won the 1912 Nobel Prize in Chemistry, for whatever that's worth. Methyl equals CH3. Me is methyl. It's just I think we've done this already. Hopefully, I think I've written methyl for CH3. Just like ethyl ET equals CH2 CH3. So what we're effectively looking at with this methyl magnesium bromide is we can kind of think mechanistically of it kind of being Me minus. That's fine. So mechanistically, what does this look like? So we have our double bond. Actually, you know what? Let's draw the carbonyl antibonding orbital. Let's change of pace. Sort of pathetic undersized lobes for the oxygen. And then I've got the methyl magnesium bond, which is already kind of extended. It's already a weak bond. Methyl has the carbon has most of those electrons. And so what I can choose to do is, instead of sharing them with the magnesium, it can take those electrons and donate them to the anti-bonding orbital of the carbon-oxygen bond. And as soon as it does that, it breaks the carbon-oxygen double bond. So if we're drawing it with arrows and mechanism, and it was acetone, and by donating its electrons to that carbon-oxygen double bond, we're breaking the carbon-oxygen double bond, putting electrons onto oxygen. There's magnesium bromide plus floating around. You can draw a bond to oxygen if you like. You don't have to. And then we add water. Because as I said, it was 1, 2, first the Grignard, then the water. Now it's going to come grab that and give us our product, which is an alcohol. So overall, we've gone from a ketone to an alcohol and added a methyl group. Now, it's not the only thing we can add to these things. Common thing for doing is something like, let's just switch it up. Yes. That work for you, Lara? Yeah. Okay. Common thing that can also have reagent that can also do this is something like a methyl lithium. Now, this is exactly the same situation. We have a metal attached to a carbon. Unsurprisingly, it reacts the same way, giving us the same product. And it could be any carbon chain attached. We could have a propyl chain, or a butyl chain, or a benzene ring, or a benzene ring with a bunch of carbon chains off of it. What we do need to make sure we don't have to worry about is no acidic. So if we had a molecule like this, we treated this with one equivalent, which means 1 mole of methyl lithium. The temptation is to draw the mechanism we just had, but what that requires is the methyl group to approach at a specific angle, that 107 degrees, to the carbonyl. And now it's going to kind of navigate into its way into the carbonyl, which is in the middle of the molecule, which is blocked. You got to navigate your way past these two guys, which are kind of like, Cerberus dogs with like slobbering mouths that are kind of barking at the nucleophile, trying to keep it away with their steric bulk. So what's faster is doing an acid-base reaction, because hydrogens are always on the surface of a molecule. So we did acid-base reactions, and CH3 minus does not seem very stable, and that's what this essentially is CH3 minus lithium plus. And so what we prefer to do is just do an acid-base. Acid-base, stupid fast. Always. And that's because you don't need a special angle. Just get close enough to that hydrogen. It's got a sphere because it's S hybridized, because that's all hydrogen can do. So you approach at almost any angle, and you're going to grab that hydrogen. You don't need the special 107-degree magic angle. You just bump into it by accident, and you're going to take away the hydrogen. You're always going to attack the OH. The only time you're going to attack the double bond is if you don't have an OH. No, it doesn't matter how long this chain is. What I'm saying here is if, so one equivalent of. So what I mean by that is like there is 1 mole of this and 1 mole of that. It's not equivalent. It just means equivalent mole-wise. Hopefully you guys ran into this term a lot in first year. And I'm now really worried you didn't. So what happens when you do this acid-base reaction? Well, you get that plus CH4, which is a gas. We'll see that in a second. But we're not necessarily done. Because what we just did up here was we said nucleophile plus carbonyl goes to nucleophile OH. And here we have a nucleophile, we have a carbonyl. And they're in the same molecule. Well, the methyl lithium attacks the OH instead. It doesn't attack the carbonyl because it reacts. The methyl lithium attacks the acidic hydrogen faster. What I should say is if acidic hydrogen, right down here, because I'm not breaking any of these bonds in here, these are still attached together. And so if I attach this to this, that'll happen. So the other option, I guess, is instead of a ring, you know what? Just the misspelling on the U almost makes it sound a little plaintive, like screaming a little bit on the inside, which is completely fair. Why doesn't this react with a different molecule? Why does it react with itself? Because what you could imagine it doing is reacting with another molecule of the same. I don't know if that's your question, Nicole, but I'm going to put those words into your mouth. And so what I want you to think about is, okay, I'm going to give you an analogy. So I'm going to just move on to the next page. I'm going to redraw this. I'm going to show two things. Because we're going to be seeing rings later, so I want to introduce rings early, and I don't want Cortana to tell me what my next appointment is. Okay. So there are two possibilities that could happen. 1, 2, 3, 4, 5, 6. We could have exactly what we just drew there. This is called intramolecular. Because it's happening within a molecule. The other thing that could have happened would be intermolecular or between molecules. So you could have had two molecules of this, and this one attacks that. We could have had that. So that's the intermolecular. And those two reactions are both possible. I'm going to say that the intramolecular is a lot faster. And that's because this is a six-membered ring. Okay, why does that happen? So what I want you to imagine, normally I do this in a lecture hall, but I'm not in a lecture hall, so I don't have that same visual. So imagine a lecture hall, because your room in your house is too small. Lots of stairs, walking places, and there's like hallways and corridors and things. Or maybe it's one of the small halls we've got here where there's like a little bit of space in between the rows. Now, what I want you to do is I want you to place two ninjas in that lecture hall. Okay. They're ninjas and they've got giant freaking swords. So I don't know if you can see me, but they're doing this just continually. Slashing up and down with their giant sword. Okay. Now I want you to blindfold both of those ninjas. And they're ninjas, so they're silent. And their swords are really sharp, so they don't make any noise. So you've got two blindfolded ninjas waving swords around in a lecture hall. Now, we're going to time how long it takes for one ninja to cut the other ninja. It's going to take a certain amount of time, right? You got two ninjas wandering around a lecture hall. You release them on opposite sides. They're swinging their swords around. And they have to swing them directly in front of them because there's only a specific angle of attack that they're allowed to make. It's a very, very regimented style of Japanese combat inside of lecture halls. And you're going to take a certain amount of time for one ninja to cut the other ninja. That is an intermolecular reaction. You've got two molecules wandering around the flask with their weapon, which is their lone pair, pointing in a specific direction, trying to bump into each other at the right angle. Now, an intramolecular reaction is if I take those two ninjas and I tie them together with a rope. Now, if the rope is too long, like really, really long, might as well have them wandering around the lecture hall loose. But if the rope is about the right length, the rope is too short, they can't turn around to cut each other. Like if I tie them together with a really, really tight rope, they just can't turn around. So that's like a three-membered ring. You don't make three-membered rings all that easily through this kind of mechanism. But if the rope is the right length to make a six-membered ring or a five-membered ring, your ninjas are going to cut each other a whole lot faster than they're going to cut some other ninja randomly walking around the room. So intramolecular reactions occur because the things are tied together. They can't get away from each other. And so they're perfectly positioned to cut themselves open. You never forget the bloody ninja. Normally, I try and give, I want to really play this out in person once in a lecture hall. We'd have to find like a flat place and blindfold people and give them pool noodles because swords are probably not safe. But we can try it out with the next batch of students when I'm next in class, and I'll videotape and put it online. So that's the difference between intramolecular and intermolecular. So why do things make rings? Because the stuff is tied together, and it's a whole lot easier to cut something when you're tied to it. We could try and recruit actual ninjas. Oh, I love the idea, Brendan. Plastic lightsabers, that's great. I think I actually have some at home. Like original 1980s plastic lightsabers with shoo shoo sounds kind of thing. Yeah. Say 2 for intra and 1 for inter. I don't think I said any number. I said intra is fast, inter is slow. Except, so do intra if get a 5, 6, 7, 8, 9 membered ring. Others about same speed, inter and intra. So these are our magic numbers, 5 through 9. Five is fastest. And then you get slower as you get bigger than 5. 5 is like, it's just the perfect size. You just minimize entropic concerns with the way that bonds can rotate and stuff. So 5 is the fastest, then 6 is a little bit slower, 7 is quite a bit slower, 8 is quite a bit slower, 9 is quite a bit slower, and 10 you're about the same size as the molecules randomly bumping into each other. Well, it did. Reduction did attack the carbonyl. Oh, in this one here. Yeah, like, you mean, can't this happen? Yeah, it can. Now you're going to make a big ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a 12-membered ring. Still can happen. What's probably more, like, it looks really promising. What's probably actually more likely, even though it looks further away, but it's just the way I've drawn it, is this guy coming, because that's going to make a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. I just drew them near each other, but there's no reason they are. They're flopping around everywhere. It sort of is, isn't it? A little terrifying, but it is interesting. Okay. So we're not going to focus too much on rings right now. This is just kind of this is coming down the pipeline, so get ready to think about rings. But right now, what I want to do is come back to this whole idea of carbonyls, because we kind of got off that. And we had, what I said is if you had only had one equivalent, that's what happened. But if you have lots of methyl lithium, i.e. greater than 2 equivalents, you are going to just get that attack that we saw. And the reason for that is the first one deprotonates the alcohol, does the acid-base reaction. In the previous case, that was all we had. We only had enough to do that. Use intra for 9-membered rings or smaller. Use inter for everything bigger than a 9-membered ring or anything smaller than a 5-membered ring, as I just wrote in the last slide. So you make rings when you can, but you don't make rings when you can't. So in this case, we have more than 2 equivalents of methyl lithium. So the first one comes in, takes off that hydrogen on that alcohol. The second equivalent, which we now have because we did not have it in that previous example, is able to come in and attack the ketone. So far we've looked at Grignards and methyl lithium, like it's all been carbons. And we've gone from ketones to tertiary alcohols. What if we want to go from a ketone to a secondary alcohol? Well, the difference between those two molecules is there's now an H here. So what I want to do is I want to add H minus, right? We added sort of CH3 minus to make these tertiary alcohols all the way above. Now I want to add H minus. Now, H minus is actually really, really basic and not very nucleophilic. So I don't want H minus itself. But we're actually going to pull up one of the things we've been talking a lot about. And that's that we're going to use boron. So that's just BH3 with an extra NaH on it. And we're taking advantage of this fact that boron doesn't know what it wants to be, right? Boron, when it only has 6 electrons, wants 8 electrons, but then it's negative. And when it's negative, it wants to be neutral, so it goes back to 6 electrons. So boron's always going between neutral 6 electrons and negative 8 electrons. And right here it's negative 8 electrons. So what's going on? So BH4 minus looks a bit like this. And we can imagine what it really wants to do is it wants to donate an H minus. So Nulia, it really depends on the mechanism. So if you're generating, so Nulia has asked a really good question, which is, when given a structure, a starting material or reagent, when should we use intra or inter after we're given them? So I think you're trying to say, when am I going to make a ring? When am I not going to make a ring? And it really all depends on the chemistry that is involved. So we're going to see a lot more examples of this. In the next couple of classes. I want to just throw this idea of the ring out there. Don't get too caught up on it right now. If you want to do some pre-reading, please do. But we are going to go into this in a lot more detail in a week or two. So we've got, but I just want to introduce this for anyone who wants to get ahead because it's not a super easy concept, and so it helps to see it a couple of times. So we have this BH4, and we want to give up some of the electrons. So you can think of this as being in equilibrium with BH3 and H minus, where the H minus is being held really close to the BH3. So it's not like a true H minus. It's not, I guess I consider that, I call it a naked H minus. It's not H with all this extra lone pair on it. It's H with, the electrons mostly on it, but still shared a little bit with boron. So we're kind of like tempering down its energy. The boron's kind of calming it down. But when it gets close to a ketone, it can't help itself. And it attacks the same way the methyl attacks. And for the same reasons, you have a positively charged carbon or a partial positive charge on that carbon. And we introduce the hydride. Then we add water for the workup. We get this alcohol. So what we've effectively done is we have reduced ketone to alcohol. So this comes down into the definition now. I'm going to end class today with this. Is the idea of reduction and oxidation. So I am a Leo the lion says grr kind of person. Loss of electrons is oxidation. Gain of electrons is reduction. So we reduced the ketone to the alcohol. And this is the terms I know that you've seen in Gen Chem, is doing electron counting on metals. And it's not as clear what we're reducing. We're reducing the carbon. So in organic chemistry, reduction often means adding more bonds to hydrogen. And we'll see that because oxidation, and this is where the whole term oxidation comes from, oxy, adding more bonds to oxygen. And when we're talking organic chemistry, it's generally what we're talking about. So let's just think about an order of compounds. We've got methane, we have methanol, we have formaldehyde, we have formic acid, and we have carbon dioxide. This is carbon at 5 different oxidation states. If we want to think about how carbon is sharing its electrons, and we want to think that with a carbon-hydrogen bond, carbon basically has ownership of its electrons because they're equal in more or less equal electronegativity. So if you're a metal person, you can think of this as carbon 0. You can think of this as carbon 1. Like if this was a magnesium making a bond to oxygen, you would say that's magnesium 1 because you're bound to oxygen. You think of this as carbon 2, carbon 3, carbon 4. And we're kind of counting the bonds to oxygen. Because if oxygen takes those electrons with it, it's going to be C4 plus on the far right hand side, which is insane. But we can think that as we go up this route, this is oxidation. And we are oxidizing the carbon. We are adding more bonds to oxygen to the carbon. Now, the opposite of oxidation, we could call it hydrogenation. We call it reduction, but it is actually hydrogenation. We are adding hydrogens back. And so walking up and down this list of things is what we're going to spend the next couple of classes on next week. So we have alkane, alcohol, ketone or aldehyde, or in a case of formaldehyde, it's kind of like almost a double aldehyde, acid, ester, amide, and then carbon dioxide. There's nothing else here. That's the only thing with 4 bonds to oxygen. Yeah. So I got just a question. Where would H2COH2 go? And what they mean is this molecule, and that's, you know what? I did not plant that question, but that is exactly what we're going to start next class with. And that's because that is in equilibrium with formaldehyde. They're both kind of ketone oxidation states. This is called a hydrate. Because it is what happens when you add water, a hydro, to an aldehyde, you get a hydrate. So normally we've gone a little bit over. I'm going to go a little bit under. What does it say under acid? Yes, that's a really good point. That is completely illegible. It says ester and amide. So I guess I should write hydrate here as well. Okay. Yeah, that's actually called an orthoester. And so Andrew said, "What about HCOH3?" And you're all allowed to hate Andrew right now. That's what's called an orthoester. We are not going to discuss them in this class. They are actually kind of important for some other stuff. Not very stable because, and the same reason hydrates are not very stable. When at all possible, if a carbon's making two bonds to oxygen, it wants to make both of those bonds to the same oxygen. It doesn't want to make them to two different oxygens. So that's why we draw aldehydes and not hydrates when the aldehyde is in water. And the orthoester really collapses down to an acid generally. I don't think that molecule has ever been made. So Mohammed asked, "What about COH4?" I don't know. I don't think that molecule has ever been made. I've never even thought about it. That's a brand new question for me. I'm going to look into that and get back to you. It's kind of like the double hydrate of carbon dioxide. And carbon dioxide is a pretty rock steady end of the universe kind of molecule. Like it's really low energy, and there's not a lot more you can do with carbon dioxide, which is why fixing it is so hard. Every every carbon source on Earth wants to become carbon dioxide because it's the lowest energy state for carbon. It's like what we do, right? We take everything, we burn it. I'll look into that. Somebody might have made that theoretically. Okay, I'm done. I'm going to stop recording, and I'll upload the lecture and the